In this lesson, I'm going to show you how to solve and calculate empirical formulas for compounds based on combustion analysis data. First of all, empirical formula is something that you learned about in Regents chemistry. It's the lowest whole number ratio between elements in a compound. You also learned about molecular formulas, which are the true formulas for substances. You learned about percent composition, which is the percentage of each element in a compound, and you should have learned how to calculate empirical formulas from percent composition data. Also, you learned how to calculate molecular formulas from empirical formula and molecular mass data. So if any of that sounds like a complete mess to you, you might want to go back and look over some tutorials on YouTube. It's really simple calculations to figure out. So anyways, back to the show. Combustion analysis is a method used to analyze organic compounds. Usually they're hydrocarbons, so by definition for organic chemistry, hydrocarbons contain hydrogen and carbon. You also might have carbohydrates, which is just with the inclusion of oxygen as well. So the way this works is the sample that you're analyzing, so the hydrocarbon or the carbohydrate, is put into a chamber and heated to very high temperatures, and oxygen is added so that the sample can combust. Now, from organic chemistry, a combustion reaction is going to take that organic compound in the presence of oxygen, and you're always going to produce a quantity of carbon dioxide and water as products. Now, when the carbon dioxide and water are produced from the combustion of the sample, those vapors, because again, this is at very high temperatures, the vapors pass into two separate chambers. One of the chambers will contain a compound that acts as a water absorber, and the other chamber will contain a compound that acts as a carbon dioxide absorber. You don't have to know those compounds. You really don't even have to know this apparatus. It's just a matter of problem solving. So what would be done is the chemist would have the mass of the water absorbing sample prior to combustion and would have the mass of the CO2 absorber prior to combustion. Then as the process occurs, this water absorbing chamber would gain mass and the CO2 absorbing chamber would gain mass as those products are absorbed by the compounds. And then by finding the difference between the initial and final masses, they could figure out the mass of water produced during the process and the mass of CO2 produced. And that information can be used to figure out the empirical formula. So I'm just going to jump into showing you a sample calculation here. It's easier just to work through a problem to show you how this works. So problem here, isopropyl alcohol or rubbing alcohol is composed of carbon, hydrogen, and oxygen. So a 2.55 gram sample of the isopropyl alcohol was combusted and produced 0.561 grams of CO2 and 0.306 grams of water. So determine the empirical formula of the isopropyl alcohol. So at the top here, I just rewrote the key data that you'll need to solve this problem, the masses of the alcohol, the CO2, and the water. And these are kind of the steps that are going to be used in this process. So we're going to figure out the grams of carbon and hydrogen produced because all of the carbon in the CO2 produced came from the hydrocarbon, and all the hydrogen in the water came from that alcohol as well. Then we're going to figure out the mass of the oxygen in the alcohol just by subtracting the masses of carbon and hydrogen that we calculated. From that, we can figure out moles of carbon, hydrogen, and oxygen, and then find the empirical formula. So now I'm going to walk you through this step by step. There's two different ways you could go about figuring out the mass of carbon in the carbon dioxide and the mass of hydrogen in the water. I will show you both ways, and really it's up to you how you'd like to do it. So for the mass of carbon, we know that there's let me change colors here. We know there's 0.561 grams of carbon dioxide produced. Then we're going to convert that into moles because we always want to get to moles somehow. So 1 mole of CO2 has a mass of 44.01 grams. And you see again, number, unit, and substance. Now, since I just want the carbon, I just want to count the carbons that are in my CO2. There's 1 mole of carbon in every mole of carbon dioxide. And then I can take that moles of carbon to grams of just carbon using the gram formula, the atomic mass of carbon. And that comes to approximately 0.153 grams of carbon are in that alcohol. The other way that you could set this up that might be a little bit easier for you is think of it as a proportion. There's some part of the CO2 sample that's made of carbon, just like there's part of the CO2 gram formula mass that's made out of carbon. If you solve this proportion, you will come up with the same answer of 0.153. So if that's an easier method for you to think of it as part over whole equals part over whole, then go for it. Now for the hydrogen, again, I'm going to run through this using factor label, 0.306 grams of water. Convert that into moles. And again, I'm using the AP reference table for all of this. Now for the hydrogen, it's different. If you think about a mole of water, there's actually 2 moles of hydrogen in it. All you have to do is look at the formula, 2 moles of hydrogen in it. Now I can convert that to grams, and since I'm just dealing with hydrogen, not a hydrogen molecule, so 1 mole of hydrogen atoms is 1.008 grams of hydrogen atoms. If you doubled this and did H2, then this mass would double as well, and it really wouldn't make a difference mathematically. This comes out to approximately 0.0342 grams of hydrogen. And again, if we set this up as a proportion, X grams of hydrogen are in 0.306 grams of water, just like 2.016 grams of hydrogen, and that comes from the fact that there's 2 hydrogens in a water molecule. 18.02. You'll come up with the same answer. So we have the mass of carbon, we have the mass of hydrogen, and now the mass of oxygen we're just going to calculate through subtraction using the mass of the alcohol that we started with. So the mass of the alcohol was 0.255 grams, and we're going to subtract the carbon and hydrogen masses, which will give us a mass of 0.0606068 technology grams of oxygen in our alcohol. So since we have those 3 masses now, we can figure out our empirical formula. So we had 0.153 grams of carbon, 0.0342 grams of hydrogen, and 0.068 grams of oxygen. So now what we're going to do is convert both of those to moles by dividing by the molar masses, 12.01 grams of carbon per mole. And that gives us about 0.0127 moles of carbon. 1 mole of hydrogen is 1.008 grams. And again, I'm using singular hydrogens here. If you doubled both of them, mathematically it would cancel out anyways. 0.0039. And same thing with the oxygen. I know oxygen's a diatomic molecule, but we're just looking at the quantity of oxygen, not worrying about molecular form here. Now, when you determine the empirical formula from this data, the next step is to take all of these answers and divide them each by the smallest answer. Oh, that should be 339. I'm noticing that right now. 0, eraser. 0.339. Okay, so we take each of these mole answers and divide them all by the smallest mole answer. So the smallest answer is this one. So everything is going to get divided by 0.00425. Now obviously the oxygen value is going to come out to 1. The carbon value at the top is approximately 3. It's like 2.97 or something like that. So it's going to round off to 3, and the hydrogen value is going to be 8. Those numbers are the subscripts in the empirical formula for the isopropyl alcohol. So it would be C3H8O with a 1. Now, if you remember anything about organic chemistry, you know that alcohols have OH groups at the end. So we can rearrange the way that this is written and say C3H7OH. There's that 8th hydrogen. But if you're just looking at the formula itself, you should be good to go if you just get the quantities correct, and even the sequence doesn't really matter that much. Here's another example of how to of a combustion analysis problem. It's the exact same format as the prior problem, so give this one a shot by pausing the video, and then I will put up all the work for the answer at the end. Okay, so this is the math behind finding the empirical formula for this particular problem. I use the method of setting up proportions to figure out the mass of the carbon and hydrogen instead of going through the factor label process just to save space. But again, either way is fine. And you should have been able to get to this point where you've divided by the smallest of the answers after you converted to moles. Now, you might think, oh, okay, I'm good. I can just round this one off to 3, round this off to 8, and obviously that's going to be 1. Unfortunately, you cannot do that. When you're that far away from a whole number, the 7.76, you cannot round off. A lot of times you'll come up with something that comes to a 0.5, maybe a 0.33, and then you would know if you came to a 0.5, you'd have to double all of your answers. If you came to a 0.33, you'd have to multiply all of your answers by 3. In the case of this particular example, the 7.76, if you think of it as 7.75, the way that you would get 7.75 to be a whole number is to multiply it by 4. If you multiply that by 4, you have to multiply all of these by 4. Now, the 2.95 answer is acceptable to round off to 3 and then multiply by 4. The 7.75 would get multiplied by 4 and get 31. And the 1 would multiply by 4 to get 4. So those are actually going to be the subscripts of the empirical formula in your answer. So the empirical formula for this particular compound would be C12H31O4. Now, does this make sense? Empirical formulas need to be the lowest whole number ratio between elements in a compound. 12, 31, and 4 do not have any common factor greater than 1, so that is an empirical formula for this particular problem. That is a tough example because you get to that 0.75 portion and you kind of get stuck. Typically, empirical formula problems in AP Chem will come out to exact whole numbers at that step, just like the isopropyl alcohol one did. Potentially, you could get a 0.5 answer or a 0.33 answer. Anything other than that is just kind of nitpicky and would really be a shady way of asking a concept such as combustion analysis. You're going to be working on some combustion analysis problems in class together. So I hope that this gave you an introduction to it so you're a little more comfortable with the process when you get to the problem solving in class.